So we're going to talk about monotonicity testing and the property testing problem about monotonicity. So I think most people in the room are familiar with the model of property testing. I'll just go through it very quickly so that we're on the same page about the notation. So we have a property here. It's a property about Boolean functions. And we want to know whether an unknown function has this property or not. Now, in general, this is very difficult, but here we relax the problem a little bit, to say, okay, you only need to distinguish these two cases where f has this property or f is far from having this property. Okay. So here, by the distance, I mean the distance between two functions. Just you draw a string uniformly at random. What's the probability they don't agree with each other? And then we measure distance between a function and a property by the distance between this function and the closest function in with this property. Okay, and the function is epsilon far if the distance is at least epsilon. So a tester for a property have the following properties. You're given an unknown function and a parameter epsilon, and you need to output yes with probability at least 2/3 if the function has this property. If it is far from having this property, you should reject with high probability. And if it's in the middle layer, if it's in the gray region, then we don't really care. So we're interested in, given a specific property, how many queries do we need in terms of, in this case, n, the number of variables of the Boolean function, and epsilon. So in this talk, I'll focus on this monotonicity property. We'll talk a little bit about the different property at the end. So a function is monotone if whenever you flip bits from 0 to 1, the function value cannot go down from 1 to 0. Okay. And this has been studied as a touchstone problem in property testing. And the first paper is by Goldwasser, Lapman, Wang, and Monotonicity. And then I think during the past 3 or 4 years, there have been a lot of papers on monotonicity testing. And in this talk, I will focus on the model where the function is Boolean. So the domain is the hypercube, and the range is 0, 1. Some of the papers here are for more general range, but this talk will focus on the case when everything is Boolean. And throughout the talk, just to simplify things, you should always consider epsilon as a small constant for 2 reasons. For lower bounds, all the lower bounds say something like, for some small enough constant, I have this lower bound as a polynomial of n. And all the upper bounds, if you look at the dependency on epsilon, it's pretty good. It's like 1 over epsilon or 1 over epsilon squared. Okay, so you should really think about epsilon as something like 0.001, or just a constant. So before going to review the results, here are like 2 very simple facts that may help you understand the problem a little bit better. So the first one is a characterization of the distance to monotonicity. So this is a typical monotone function. And for far from monotone function, you may have all these zeros and ones kind of mixed. But this characterization really helps. It says that a function, if epsilon far from monotonicity, if and only if there are epsilon 2 to the n, many violating edges. So naturally, what is a violating edge? It's an edge where you flip a few bits from 0 to 1 to get y from x, but somehow fx is equal to 1 and fy equals 0.
It's not edges in the hypercube.
This is not necessarily an edge. Yeah, it's violating pairs. Okay. Yeah. So, but they should be disjoint. Each pair should give you a violation. If you see any such pair, you can just reject the function. So this characterization we'll use later in the talk. And the other thing is, like, the first thing I learned when I worked with Rocco on this problem is something common about such Boolean function is you should always focus on the middle layers. By middle layers, I mean strings with Hamming weight half n plus minus root n. Okay, you can make the root n bigger, say 100 root n, because these middle layers contain most of the points. So you can always do this truncation by setting the function to be 1 above these layers and 0 below these layers. This doesn't really change the function that much. After doing that, we can safely assume that the tester that we are interested in should only query points within the middle layers. Okay, so from now on, we should really think about the hypercube as these two triangles cut off, like only about the middle layers. Okay. So here are the upper bounds. The first upper bound is comes from this really natural tester, the age tester, where you just sample a random age by sample first a random string and flip a random coordinate. And you just check if this is a violation age. This, for example, would be a violating age. You just repeat a few times. If you see one, you reject. If you don't see any, you accept. Okay. So clearly, this is a one-sided and non-adaptive tester. The main question is how many ages you need to sample so that you have a reasonably good probability to reject if the function is far from monotone. And this was shown by the paper I mentioned earlier, the Goldberg et al. Paper. They show that n over epsilon queries are good enough. If you try this n over epsilon times, you will get a violating age with high probability. But this is also there is a matching bad example. If the function is an anti-dictator function, to get this special variable xi, you need omega n queries. To do it better, here is a natural generalization of the age tester where we just do pair tester. So you sample a random string and flip, let's say, t bits from 0 to 1. I'll tell you how to pick this t later. And if you see a violating pair, you reject the function. If you try a few times, you don't see any, you accept the function. Again, this is one-sided, non-adaptive. And it turns out the right way to choose this t is to choose it uniformly over all these powers of 2 between 1 and root n. You never want to go beyond root n because we only work in the middle layers. But you also want to, in some way, make the distance kind of evenly spread out. So in particular, this covers the age tester, with probability 1 over log n, you're actually using the age tester. But in general, it covers more distances. So the first analysis, the breakthrough was made by Chakrabarty and Seshadri, where they pushed the upper bound from linear to n to the 7/8. And in this paper by Kot, Mainzer, and Safra, they gave a root n upper bound, and their proof used a directed analog of isoparametric theorem of Talagrand. I think there was a talk. I think Kot gave a. I watched the.
But people replaced.
But yeah, I remember at Columbia we actually organized a seminar. We watched the video together. Yeah. Okay.
Yeah, it's definitely on our video site.
Yeah, you should watch it. It helps a lot if you want to understand that paper.
And this is right for non-adaptive.
For non-adaptive, yeah. So these are the. Yeah, I think it's a problem with the computer.
Is this the isoparametric theorem, the one where he defines this weird distance to a set?
There is we have several of these, but but it's quite a bit of technical work to get this directed version. It's a non-trivial definition also. Yeah, it's a beautiful paper.
do we have maybe a mouse I can use? Because I don't know why I cannot use the.
Are you using a regular PDF?
Yeah, just regular PDF. Sorry.
Just put your. I got it. Put your presentation on my. Here.
Oh, now it works. I think it's because
It
of
might
the
be
pointer.
because of the pointer. Well, then you
Yeah.
could just click through your slides using this and
Sure.
use this as the pointer.
Sure.
Okay?
Sure.
Maybe that'll.
Okay. So now let's go to the lower bounds. So the first lower bound is by Fischer, Lemon, Newman, Raskolnikova, Rubenfeld, and Samorodinsky. And they show that if the test is one-sided and non-adaptive, then you really need Rudin queries. Okay? And the proof is using the following random anti-dictator function, not xi. And let's go through it very quickly because I think even the adaptive lower bound has some idea from this proof. So this is the function. Forget about these parts. Basically, we ignore the points outside of the middle layers. Inside the middle layers, you just take the anti-dictator function. Now think about how the pair tester would work. Each pair would help us like search or cover Rudin indices. So Q pairs can help us cover Q Rudin variables. So if you want to succeed with high probability, you need Q to be Rudin. Now you can say, okay, what if I can carefully pick Q points and look at all the Q square pairs? Now, one bad thing is the tester has to be one-sided. So it's not like an arbitrary pair can help you cover anything unless one dominates the other. Okay?
Can you say it slower?
So
What are you trying? This seems easy, so now you point out that it's not so easy.
yeah, because you can potentially pick, let's say, Q queries and say, look at all the Q square pairs.
Oh.
Maybe together these pairs may cover for you more than Q Rudin. But you have two restrictions, right? The first restriction is this is not adaptive, so you have to really fix your queries in advance. The other thing is the tester has to be one-sided. So if a pair of your points are not comparable, like one does not dominate the other, then it doesn't really say anything. So only the pairs that one dominates the other say something, and you can use that to say, okay, in general, Q queries only cover Q Rudin. It's like a one-paragraph argument. So this is for the one-sided non-adaptive case. And there is a very simple adaptive algorithm to beat such distribution. You just do binary search, right? You randomly pick 2 points. Most likely you will get a 0 string, 1 string, and you do binary search. That would give you this special variable xi, and that's it. Okay, you can spend log n queries to find out this I.
If you know that the function is an anti-dictator, but
Yeah.
you don't know which one.
Yeah, if you know this is a bad distribution where your function comes from, you just want to find out this xi. So later we'll see how the distributions used in the adaptive proof like avoid this, like make the job much harder for a tester, for even an adaptive tester.
Another question. So
Yeah.
is the epsilon dependency here also tight in terms of lower bound?
Yeah, for the lower bound, we usually, I don't think any of these lower bound really put any dependency on epsilon. All the lower bounds say there is a there is some constant epsilon. Like if you want to distinguish in property, epsilon far from property, you need some function of n, many queries. So I don't think the dependency on epsilon is tight.
Itself in particular doesn't seem to have any epsilon dependency. You can't really make the number of variables to go more than one.
Yeah, I
Seems to
think
be
so.
the worst.
I mean, there is some dependency, like this function give you some epsilon, right? This function is epsilon far from monotone for some epsilon.
If you have
So-
100 root n or something.
Yeah, you
Yeah.
may want to make it 100 root n if you want epsilon to be small.
Also, the upper bound by quotes has a log n or something in it, right?
Yeah, I'm hiding log factors. Yeah, there were log factors. Yeah. So then we had this result about two-sided non-adaptive tester, and which basically says even if you allow the tester to be two-sided, you still need roughly root n queries. Okay, it's not all the way to root n, but almost. And it turns out that the function we use are very simple functions. They're linear threshold functions. But these functions will never give you any reasonably good lower bound for the adaptive model, because the binary search thing kind of works again for these functions, and you can get a very good tester for LTFs. By this, I just mean, you know, if your function is promised to be an LTF, the problem is much easier. So these two will be the results that I'll focus on in the rest of the talk. The first one is a breakthrough made by Bellows and Bliers. It's the first polynomial lower bound for adaptive monotonicity testing. And they prove a lower bound of n to the 1/4. And we recently improved it to n to the 1/3. So the plan for the rest of the talk is I'll actually spend, I think, 20 minutes on their proof. We'll basically see most of the details behind the proof. Actually, I will present it in a way different from the original proof. And we'll see why it, first of all, we'll see what the functions they use. And then we'll do some analysis. And we'll see where the bottleneck comes from. Like the tester can no longer do binary search, but the tester can still can use this so-called, what I call like quadratic speed up strategy, where the tester can use Q queries to cover roughly Q square root n things to search for something bad. So in some sense, this bottleneck of n to the 1/4 is like intrinsic to the functions they use. And then we have to get some harder functions to get this n to the 1/3 lower bound.
We would be looking at the one-sided testers?
Two-sided, yeah.
Is there a better lower bound for one-sided vector?
No. That's actually a good question. Like, I would be really happy if any of these things can, you know, like root n lower bound, but just one-sided, yeah. Right.
What do you believe to be the truth?
I think so, yeah, if you ask me
So
to.
root n you think root n is greater?
Yeah, root n should be the lower bound even for like two-sided adaptive, yeah. But okay, we'll see where we get stuck in this 1/3, and I don't know. Definitely you need even harder distributions. So just some notation. This is not really standard, so I'll mention it here. So I'll reserve these little x1, little xn for variables. So these are variables that I'll use when I describe these functions. And I will use these capital X letters, mostly capital Z, as a string in the hypercube. Now in the talk, we'll be interested in, you know, when I have a bunch of strings, what's the number of common 1 entries they have, and what's the number of common 0 entries they have. So I will kind of abuse the notation a little bit and use Z to denote the set of 1 entries of Z, and the Z complement as the set of 0 entries of Z. So this allows me to, you know, write down, you know, the common 1s and the common 0s of strings in P using this notation.
It's a union. Common usually is the intersection.
Oh, sorry.
You mean
Yeah, I mean intersection. Yes,
you mean
intersection. I mean intersection in both. Yeah, intersection. So common, 1 entries, common 0 entries.
And
Yeah.
P is not necessarily the property. P is some set.
P is just some set, right? Yeah, should not use P. Yeah, but P is just some set. We'll define later. Yeah. Okay. I'll remind you when I use this notation. So we'll just do the Minimax principle. We'll reduce the problem to the design of a pair of distributions, and we'll say, you know, no deterministic algorithm can distinguish these two distributions unless it has a lot of queries. So in our problem, the first distribution, DES, will be supported on monotone functions, and the no distribution will be supported on functions that are far from monotone. And then we want to say any adaptive deterministic algorithm using Q queries with some upper bound on Q cannot you know, have a bigger advantage of accepting F from the yes distribution compared to G drawn from the node distribution.
And you have the mostly there, so the negative distribution will have some,
Yeah. Yeah.
but few.
Yeah. Let's say omega 1 probability, omega 1 far from monotone. Okay. So this is just a typical approach. Like, we look at an algorithm, which is just a decision tree with steps q. And I want to show that for any leaf in this tree, the probability of F reaching this leaf has little advantage over the probability of G reaching the leaf. Now, in general, like this is just very standard in the literature. Like in general, this is not true for every leaf. So you kind of, divide the leaves into good ones and bad ones. And you say that if F is drawn from the yes distribution, with little or 1 probability, F reaches a bad leaf. And for the good leaves, you somehow manage to prove this inequality. And then these two together will give us what we want. Okay. So later we'll define good leaves and bad leaves, and we'll prove this for the good leaves. And this is just rewriting things. What is a leaf? It's just a bunch of queries and their results. And this is the probability that FZI equals BI. And that's the probability for the node distribution. Okay. So here is the function Bellows and Blythe used for their yes distribution. It's this so-called Talagrand random DNF function. So let me describe to you how you draw a function. You first will write down this tree with the top, with the root being an OR gate. And you have 2 to the root n many AND gates. And each AND gate has root n many variables. Now to draw a function, you just draw this tree. And for each leaf, you randomly put one of your variables there. And if you're done with this huge tree, you get your function. So this is clearly monotone because it's a monotone formula, even though it's huge because it has 2 to the root n many terms. Now here is the no function. Everything is the same. You draw basically the same tree. You draw those variables in the same way, except that you flip the last variable of each term. You make it negated. Okay. Everything else is the same. So I want to say this is slightly different from the distribution Bellows and Blythe used. What they used is, generate the same tree for the yes case, and then you draw a set of variables S of size root n, and then you just every time you see a variable from that set, you flip it. Okay. This way, they can use results from noise sensitivity to quickly conclude that these functions are far from monotone. But I think here we're doing it differently. And this helps us make all the terms kind of independent from each other. There is no correlation between these terms. And we'll see this is also far from monotone. Okay. So here is some intuition why these functions are far from monotone. Let's just see why these parameters are chosen this way, why it's root n and 2 to the root n. Let's take a string in the middle layers and calculate what's the probability of G of Z equals 1. So to make it 1, you have to satisfy one of the terms. So we have 2 to the root n many terms. For each term, you have this product which gives us the probability. Now Z is in the middle layers, so everything here is like half plus minus 1 over root n. And if you take this to the power of root n, it will give you like 1 over 2 to the root n times something constant. I mean, constant, like both constant away from 0 and constant away from 1. Okay. And this way you can say, okay, a typical point in the middle layers, if you draw a function, it's 1 with probability constant. You can also show that it's 0 with probability constant. And you can further show that the probability it satisfies a unique term is also a constant. Okay. Now I want to use the board just to say a little bit like what I think about this in a picture. I did not have enough time to draw this on my slides. So these are the middle layers. Right? Now you take a Ti, but let's say Ti prime. which is ti, but with the last variable removed. So it's really root n minus 1 variables. Everything is monotone. Okay. Now, each of these ti prime defines for us like a small cube. And there are 2 to the root n many cubes. So take this one. This cube contains all the points z, such that ti prime of z equals 1. Okay.
How about this joint?
They are not, they don't overlap too much, and together they cover a constant fraction of the middle layers. Now, we set ti prime. In addition, if you look at ti not only has ti prime, but let's say it has this variable xk negated. Now, if you look into this cube, you can divide it into 2 parts according to xk. So this is the part where xk equals 1. This is the part where xk equals 0. And this part is actually have function value 1. And the part below has function value 0, because this variable is negated. Okay.
So the opposite.
Right, sorry, the opposite. Yeah, 0, 1, because this function is negated. Okay, and this gives us like a
Does this rely on the uniqueness of the?
this rely on the uniqueness, like, most of the points should not be covered by any other cubes. If it's not covered by any other cubes, this should be true. But let's say, it's not covered by any other cubes. Then all these are violating edges, right? Basically, you flip your xk, you'll get a violating edge. And these edges are disjoint because these cubes are mostly disjoint. So this will give you 2 to the root 2 to the n, omega 2 to the n many violating edges that, using the characterization, tell us it's far from monotone. Now, I also want to use this picture to say a little bit like what's the difference between this construction and, let's say, just the n-time dictator function. So let's say I made one query, and I found out a point z. Let's say it's a 1 string, so I know it's somewhere in this part of a cube. Now, if I want to find a violation, I need to somehow find this k and flip it. Right? So, but I cannot do the binary search, because if I randomly pick a point, let's say y, very far away from z, it's most likely has nothing to do with this cube. So if you do binary search, you will get a coordinate, but it's most likely has nothing to do with k. So you're in this dilemma that you want to find a k, but if you want to do binary search, you don't want this point to be very far away. And if you flip, let's say, root n points, root n bits of this string, most likely you will already be far away and not in this cube. So the binary search does not work, and we'll see that in general, no adaptive algorithm works if it has less than n to the 1/4 queries. So here is the goal again. Now we have defined these 2 distributions. Yeah.
So for this distribution, the answer is n to the 1/4.
Yeah, it's actually there. I'll talk about this. There is a one-sided tester that rejects with high probability, so with n to the 1/4 queries. So here is the goal again. We take any leaf with these strings and these answers, and we want to compare these 2 probabilities, one for the yes distribution, one for the no distribution. Now the difficulty is like these are very difficult to analyze events. So what you do is just decompose it, make it simpler events. Then we want to compare those simpler events. So here the way to decompose it is I just allow the oracle to return to you not only the value of fz, I also, if fz equals 1, I also allow the oracle to tell you which is the first term that gets satisfied. Okay, and this is basically looked like this table. So let me explain this table.
That's a lot of information. It's like root and bits.
That's a lot of information. Yeah.
And it's still not helping.
Yeah, that's right. Even if I give you, the index, like which term, that doesn't help. So this is what we call a signature of a bunch of queries with respect to your function. F is from either the yes distribution or the no distribution. So you have a row for each query, and you have 2 to the n plus 1 columns. The first column is the value of f, and the second column basically tells you does z satisfy T1 or not. Okay, so for each row, let's say this z6, the oracle will tell you, okay, you satisfy one term, so your function value is 1. But I also tell you you satisfy the third term. That's the first term you satisfy. Okay, then you can mark your table by marking these as zeros, because I know z6 does not satisfy these terms. And after T3, I don't really care. Right? It could be 0, could be 1, so that's why it's marked a star. Okay. Now, one thing I want to point out is like this trivial fact, but we'll use.
This is in your random choice, the order of the z's. The algorithm doesn't know what the z's are.
The algorithm does know what the z's are. Think about this as a leaf, and the algorithm queries these strings one by one. So we are focusing on a leaf. So I have this sequence of queries.
The algorithm doesn't know the t's.
The algorithm doesn't know the t's.
So it can draw this table, but it doesn't really know what they are.
Yeah, yeah. So we'll talk about, if I draw a random term, how likely to get that column. Yeah. Yeah, so the algorithm just knows the table, but not the terms. So one thing is the number of ones is clearly at most acute, because I'm only telling you the first one entry. But this will be something we use later. And this just reminds you the goal. Like I want to show for any such table, the probability you get from the yes case and no case are roughly the same. Okay. Now, if you have these two quantities that we're interested in, you just, they're just products, because the columns are all independent. The terms are all independent. That's the thing that I think is nice, because if you do the Bellevue-Blaise way, they're not really independent. So let's use Talagrand T as the distribution where you draw a random monotone term. Root and variables, everything is monotone. And this is the distribution where everything is the same, but you flip the last variable. Okay. Then what's this probability? This probability is a product of things, one for each column. And you ask, what's the probability if I draw a monotone, random monotone term? What's the probability I get, column J? Okay. So for example, for column 2, that's the probability of drawing a random term. Then Z1, Z2, Z3 satisfy this term. Z4, Z5, Z6, Z7 does not satisfy this term. Right? This is an event, and we're interested in its probability, and we want to compare these two cases. Okay. Now let me simplify things a little bit by only focusing on these, what I call non-trivial columns. A trivial column is a column where you only have 0 and stars. A non-trivial column is where you have at least one entry in that column. Let me say a little bit why I want to ignore those trivial columns, because in some sense, let's take this column as an example. What's the event? The event is you draw a term, and all these strings, none of them satisfy the term. I want to say intuitively, this event does not help you that much in distinguishing the two distributions, because if I take, for example, Z7 as an example, let's say I draw a random term. Most likely, it does not satisfy the random term. And also, most likely, it does not satisfy the random term, not because the last variable. It gets killed maybe way before the last variable even occurs. So the last variable doesn't really reveal that much about the difference, whether the last variable is negated or not. Okay, and on the other hand,
so this may be the input Z with very few ones or something like this.
yeah, but you have to be in the middle layers. So it's really balanced, half ones, half 0. Yeah, that's the reason why I want to ignore these 0 entries. And also, these columns are not really the bottleneck. meaning that even if you allow the algorithm to take root n queries, I can show you like these columns, the ratio is 1 plus little of 1. So if it's all about these columns, you can survive up to root n queries. Okay? The bottleneck occurs about when we talk about these non-trivial columns. Okay? So let's focus on these non-trivial columns. And I'll use P1, P2 to denote the following decomposition of your partition of your strings, input strings. So P1 contains all the strings with a 1 entry in the first non-trivial column. P2 contains all the strings in the second non-trivial column, going from left to right. So in this case, P1 contains these 3 strings, P2 contains these 2 strings, and let's compare these 2 probabilities. Okay, and if you look at these 2 probabilities, again, I'm hiding something, right? If I sample a random term, the probability for this column, it's not just the strings like Z1, Z2, Z3 needs to be 1, but it also, for these strings, the result should be 0. So again, I'm hiding something, but I want to say those 0 entries don't really matter that much. It's really the bottleneck come from these 1 entries. So let's forget about these 0 entries. Let's just focus on the event where I draw a random term, and these 3 strings satisfy the term. And let's do this for each of the PIs and compare these 2 sides. Okay. Now these probabilities are really easy probabilities. We can, okay, I get the intersection right. So okay, so these are easy probabilities which we can write down explicitly what these probabilities are. So for example, what's the probability that all the strings in PJ satisfy a random term? Is just take the intersection of the common 1 entries and divide that by n, take the power to the root n, that's exactly the probability. For the no case, everything is the same except the last case where you look at the number of common zeros, not the common ones. So if you take the ratio, everything will cancel out. And the only thing left is, here is, I put the no part on top. This is the yes part. So this is the number of common zeros divided by the number of common ones. And you multiply over different PJs. If we can prove this is at least 1 minus little of 1, we're done. Okay. But in general, this is not the case. If I can give you a bunch of strings all in the middle layers, but their common zeros is a lot less than the common ones. I can make it really unbalanced. Okay. So this is where we are going to put the condition on the signature. This is the good, bad condition. And then we'll see the bad signature is a little O1 fraction. So we focus on the good signatures, and the good signatures help us bound that ratio. Okay. So what is a good signature? A good signature is, let's say we focus on this non-trivial column, and we go down, this rows 1 by 1. Okay, think about we're making these queries 1 by 1, and it's good if every time a new string is added to the PJ. For example, let's say the time when Z3 is added to P1, the number of common ones only drop by at most roughly root n log n. If it's not, if there is a column where you added some string in the middle and this dropped by more than root n log n, we'll call it a bad signature. Okay. And I want to say the probability of a function drawn from the yes distribution giving you a bad signature is tiny. Okay. And let's take this green entry as an example. Before adding this entry, we have P1 equals, containing Z1, Z2. Adding this entry suddenly make their common ones drop by a lot. And I claim this is very unlikely just because before seeing this Z3, the term is like uniform over the intersection of Z1 and Z2. There is, every indices there looks the same, so your term is really uniform there. And I have root n uniform things, and suddenly I can cut off, root n log n things and say none of your root n random indices is there. That's a very unlikely thing. it's very unlikely for you to make such a big cut, and and turns out none of the variables is there. Okay.
So this is really a message to an algorithm designer who is fighting these distributions. It doesn't make sense in the adaptive choice of new inputs to make such a drop.
Yeah, it doesn't make sense to
miss a lot of the yes.
Yeah, if you make such a big step, you will most likely go to somewhere that is irrelevant, a different cube. So this allows us to focus on the good signatures. And so what happens with a good signature? Just by definition, we know that at the end, when we look at this number of common 1 entries of pj, because each time when a new string is added, it goes down by root n log n. So it should at the end be at least half n minus the size of pj times root n log n. Okay? But remember, this is not the quantity that we want to lower bound. We want to lower bound the number of common zeros. Right? That's what on top of the ratio that we're interested in. But if we have this, it tells us at least every pair of strings in pj have Hamming distance at most pj times root n log n. And this would be a safe lower bound for the number of common ones. Sorry, the number of common zeros. Okay? And on the other hand, you can actually make this happen. Like you can actually carefully choosing your queries to get this quadratic thing, like spending q queries and shrink the common zeros by q squared root n. Okay? And if you think about it from the algorithm point of view, you're really searching these entries for that variable you flip. Okay? So this is also like intuitively why I will later say, this idea give you an algorithm of n to the 1/4. Okay?
So could you repeat how the algorithm can take advantage here?
Yeah, so for example, let's say these are the zeros, these are the ones. The condition, the goodness condition only says each time the ones can only shrink by root n. But you can say, okay, let's spend half pj many queries to shrink it root n by root n. And then you can speed up. So the first half q queries I made is just to shrink the common ones, root n by root n. After half q queries, this already gets shrinked by half q times root n. But our goal is to shrink the 0. So from the second half of queries, starting from there, I can make a query like, I'm flipping all these to 0, and I'm flipping a matching size part to 1. This way, I can shrink the 0 part very quickly. I'm not shrinking the part, one part anymore, but I can shrinking the 0 part very quickly. So you can actually get this quadratic phenomenon when you shrink it. Yeah. So I'll refer to this thing as the quadratic speed up. But for now, let's just plug this in, this ratio that we're interested in lower bound. What's left is not really interesting. You just get here, and it becomes clear that for the worst case is put all the q queries in one pj, let's say p1. Don't spread it out, just put them in one pj, and then you'll get this 1 minus q squared over root n. So if q is n to the 1/4, you get 1 minus lid over 1. Okay. So that's basically everything in the n to the 1/4 lower bound. And I said earlier, the analysis is tight. You can actually come up with a one-sided tester that reject the node distribution with high probability. Okay. The tester basically, like I said, spent all the queries to attack one term, and somehow using this quadratic speed up phenomenon to search through q squared times root n many variables in order to find that special variable you flipped. If it's in one of these variables, you will see a violation. Okay. So we definitely need harder distributions. And the one we used is this kind of like two levels of Talagrand functions. So let me define this function for the yes case. For now, let's forget about this second layer. The first layer is exactly a monotone Talagrand random DNF. Everything is the same. So to output 1, you have to satisfy one of the terms. Okay. Now, in addition, for each term, I'm creating an independent random Talagrand CNF.
Only one input to this AND gate.
Yeah, only one input goes to the AND gate. So now to satisfy this term, let's say, you not only need to satisfy the original random term, but also the new Talagrand CNF should also give you 1. Only if that happens, you output 1 in the whole function. Okay. Okay. Now, to make it easier to analyze, I am actually adding this extra condition that is that make it a little bit different from just this picture. So it says that if I have 2 terms satisfied, at least the 2 terms, then you don't need to go to the second level. Just forget about the second level. It's already 1. If you don't satisfy any term in the first level, you're definitely 0. If you satisfy a unique term, you need to go down to the second level. In some sense, it's like an addressing function. Like the first layer really tells you which second level Talagrand function you need to look to. If you go through the first layer, the value is decided by the second layer. Maybe you don't even go through the first layer, then you don't really see anything from the second layer. We'll see that the non-monotone part only comes from the second layer. Okay. So this is the non-monotone, the far from monotone part. Everything is the same except that we flip all these last variables of each term. Okay. And we do the same thing, like if you satisfy 2 terms, you don't even go to the second level. Okay. So let me say a little bit like why these functions are far from monotone and why they are kind of harder than the original function. So in this picture, now you don't have 2 to the root n cubes, small cubes, but now you really have 2 root n cubes. Like each cube is defined by a term ti and a clause cij. So how can you enter this cube? You have to somehow satisfy ti and falsify cij. That's how you get to enter this cube, and there are 2 to the 2 root n many cubes. They cover all the middle layers. And why it makes harder for the for a tester, because now if you want to like search something within this cube, you not only need to satisfy the term, but you also need to falsify the clause. And we'll see that basically this little change make the tester prevent the tester from fully applying the quadratic speedup strategy. Okay. But these are the functions we use. Again, this is like what I sketched earlier. Now, if you want f to output 1, either 2 of the terms are satisfied, then you don't need to go to the second layer. Or a unique term is satisfied, then you go to the second layer, look at the function hi, and it's also 1. In this case, you output 1. Okay. You output 0, either no term is satisfied, or a unique term is satisfied, and the hi tells you it's 0. Okay. So in the rest of the talk, I will assume that all the queries are of this red type. You made a bunch of queries. Every query satisfies a unique term. And if you go down the second level tree, it falsifies at least 1 clause. Okay. These are the most interesting queries because, for example, these 2 are definitely not interesting because you never get to see the second level at all. This is also not as interesting as the red one because when this happens, it says that all the clauses are falsified, right? Which is like, like what I said earlier in the table. I don't care about 0 entries. I don't care about strings that do not satisfy a random term because that's most likely that should be the case. and it doesn't really help us distinguish the two distributions that much. So let's focus on these strings.
Question. So on the second level, we have ORs, right?
We
So
have
HI equals to 0. Well, what does it mean that one of them is falsified?
it means that one of the clause outputs 0. If this is 0, it means one of the clauses.
Or it means all of them are 0. It's all.
It's end of ORs.
But the second level is OR. Oh.
The second level we switch it. Yeah, we need to switch it. Yeah. So here is the new picture of what a signature looks like. So first of all, we need to partition such strings into P1, P2 according to, which terms they satisfy in the first layer. Like P1 here has all the strings that satisfy T2. Remember, we're interested in strings that satisfy a unique term. So this partition all the strings into P1, P2, so on and so forth. And once we follow P1, P1 gets split into Q11, Q12. Like Q11 is all the strings that share the first clause that they falsify. Okay? All the strings here falsify this clause, make it output 0. And I have another bunch of strings that falsify this clause. So I have this way to decompose P1 into these sets Q11, Q12. Okay? And again, we're interested in the two probabilities. We get this table for the yes case, and we get this table for the no case. And if you write it down, it's really just these probabilities. This is one probability for each term, for each pi. This is one probability for each qij. And the blue part will cancel out because the first level, the two sides are really the same. So it's really the qij's that we're interested in, and we need to compare. And if you take the ratio, it's very similar to what we did before. We get this exact expression. So we need to basically lower bound the number of common ones of z's in qij, and then multiply everything over qij. Okay. So let's do the same thing. Let's say a signature is good if you every time add a string to qij. Now it's the number of common zeros cannot drop more than root n log n, because Cij is a clause, so it's really about the number of zeros that cannot drop too fast. Okay? But this doesn't give us anything better because, we can say the number of common ones is still at least dropped by Qij squared times root n, but we still get this quadratic thing, and it will still lead to into the 1/4 lower bound if you plug this into the ratio. Yeah, so we just use the first layer to do the same goodness condition and say the number of common ones in the first layer for pi cannot drop too fast, cannot drop faster than root n times log n. And this tells us if you look at pi, the common ones cannot drop too fast, at least half n minus pi times root n. Now let's look back to check this quantity that we're interested in. On the one hand, we have this because of the goodness condition on qij's. On the other hand, this is at least this because qij is a subset of pi. So this is also at least half n minus pi times root n log n. Okay, so it's lower bounded by two things. And the difference is here it drops quickly. It's a quadratic thing. But for pi, it really drops linearly. And if you plug in everything, this is the ratio we're interested in. And if I fix for you the size of pi, what's the best way to distribute qij? It doesn't make sense to make any of the qij bigger than root n pi. So every qij will be of size root pi, and we'll have root pi many. Okay? So this way, if you plug in everything, you will get this quantity. So you can see that the algorithm cannot do fully the quadratic thing. but it's something like q to the power of 1.5. And that would give you the 1/3 lower bound. Okay. So in some sense, I think the message is really this distribution is still not hard enough for the for an adaptive tester. If you want to prove Rudin lower bound, you really want to say something like spanning Q queries. You can only search for like Q times Rudin things. But here we're still not there. And also, I think one easy generalization is make the tree like let's say 3 layers, 4 layers. I think it doesn't work that well. Like for the 2 layers, we have also a one-sided tester with 1/3 lower, 1/3 upper bounds. And even if you extend it for, let's say, 100 layers, it doesn't work that well. Still probably 1/3. So definitely we need some harder functions to close the gap. And I want to mention a few things about the other property, which is called uniqueness, which is very closely related to monotonicity. The only difference is now every entry, every variable is either monotone increasing or monotone decreasing. Like you don't know which direction it goes. And we have this upper bound, linear upper bound. And for one-sided non-adaptive tester, we can prove this n lower bound. And it would be great if we can push this lower bound at least, above Rudin. That would say, uniqueness is strictly harder than monotonicity.
So this is the square root n lower bound for two-sided tester is in some sense analogous to the 1/4 lower bound, because the upper bound here is linear. It's the same.
Yeah, it's kind of This one, the construction is actually very simple. You just take the original distributions of Bell-Abson Bliss and apply a random orientation on each of the coordinates. That will give you like this quadratic thing. So I guess I would, conjecture this thing should be n, but we still have this gap there. Okay, so that's everything in the talk. Thanks for the attention.
Questions?
Okay.
I have a question. So
Sure.
you're in a friendly audience. Of course, it's on camera, but
Right.
who cares about monotonicity?
I really don't know. I just feel like it's a natural property to test, but I don't know how to say more than this. For example, I feel like if you are testing, let's say, home tasks, people may care more, but monotonicity, I don't know if there is a application where you do need the function to be monotone, and this testing would serve as a pre-process for that. But in general, I don't. Other than the fact that there are these interesting things going on in monotonicity, just mathematical things. But other than this, I don't have any reason to say like why it's different from any other property testing problems.
Do you know if there were applications to the, for example, the directed versions of the, so obviously the proof techniques are interesting. Do you know if there were applications to the directed Talagrand inequality?
Like any of these lower bound construction, can you say anything about that inequality?
I mean, the Talagrand, the original Talagrand inequality is sort of useful in various combinations.
So we're thinking about possible ways to use this 2-layer Talagrand function, because for me, I have not seen it in the literature before. So we're thinking about using it to prove some lower bounds for other functions like Hongta or K monotonicity. To me, like Hongta would be more interesting, but compared to monotonicity. But mathematically, monotonicity testing is really interesting. I think there are all these things have been developed around it.
Any more questions? Okay, thanks.
Um,